Hello friends, how are you doing? It's Igcse.science.notesz on YouTube, and I have all of the notes screenshotted or written down and uploaded or posted in my Instagram account Igcse.science.notesz. This is part 3 for electrolysis. We have 7 points to do. The first point is a very quick recap about what we did in part 1 and in part 2. So we basically in part 1 talked in details about electrolysis, the definitions, the terms we should know, the molten compounds, the concentrated compounds, the diluted compounds, and aqueous ones. We also in part 2 we did a quick recap and we did the electroplating, and we finished all points in electrolysis. We just have how metals are extraction of aluminium and iron, uses of aluminium and alloys, and the purification of copper. So let's start first by how metals are extracted. So basically metals, as I told you before, we have this reactivity series. So basically this is the periodic table. As you can see over here, this is in one group, and then we have carbon itself alone, and then we have the hydrogen is when solving for electrolysis. However, now we don't have it. We have zinc, iron, tin, and lead, so that is Pb, anyways, together with copper. And then we have silver, gold, and platinum together alone in another group. So why is that? As you can see over here, when you go up, you increase the reactivity. That's why elements above carbon, which are potassium, sodium, lithium, calcium, magnesium, and aluminium, all metals above carbon, because of their high reactivity, they are extracted by electrolysis. So these are extracted by electrolysis due to their high reactivity. Okay, and now we have carbon as carbon only, and then from zinc to copper, which is zinc, iron, tin, lead, copper, which are metals below carbon. They are extracted by heating them with carbon in blast furnace. So they are basically the metals below carbon are extracted by heating them with carbon in a blast furnace. So as you can see over here, we're gonna have the extraction of aluminium by electrolysis and extraction of iron by carbon. We're gonna explain both ways. So for metals above carbon are extracted by electrolysis due to their high reactivity. Metals below carbon are extracted by heating them with carbon in a blast furnace. So we still have silver, gold, and platinum. These have very low reactivity. These low reactivity metals do not need to be extracted because they are so unreactive. You'll find them on their own, native, not in a metal oxide. For example, copper can sometimes be found native. Okay? So basically copper can sometimes be found native. However, these are purely, like, not purely, but they are natively found. So they do not need to be extracted anyways. Very unreactive, that can be found native, and so no need for extraction. Copper sometimes is found native too. Let's do now extraction of aluminium. So basically, aluminium is very easy. It has an ore, and this ore is called bauxite. Bauxite is a red-brown solid, and aluminium oxide mixed with impurities, for example iron 3 oxide, is extracted from the earth. So basically, the extracted aluminium oxide is then treated with an alkali, which is maybe like sodium hydroxide, to remove the impurities. And so this results in a white solid called alumina. It's either called alumina or aluminium oxide. So the alumina is then transported to huge tanks. The tanks are aligned with graphite, and these acts as cathode. So we said that aluminium is above carbon, and so is done by electrolysis. That's why we're going to talk more now about electrolysis. We have the normal part. We have this as well. This is cryolite. We're going to talk about it now. We have here this tube. It has the aluminium extracted. We have we said that the huge tanks are lined in graphite as well. Here is electrode 2. So the graphite lining is the cathode, and here in the middle, like this, we have block of graphite hanging, separate blocks of 3 blocks or something. We're gonna draw 3 anyways, of graphite electrodes hanging, and these are the anodes. So actually the alumina melts on 2000 degrees, and so that's why we have the cryolite. Why do we have the cryolite? The alumina is dissolved in molten cryolite because it lowers the melting point. It has Na3Al(F6). This is how we write it. So why? Because it lowers the melting point and it conducts more. Okay, so the alumina is then dissolved in the molten cryolite. This lowers the melting point and increases the conductivity. Why? To save 2 stuff: money, time. Electricity is passed and electrolysis begins. Electrolysis, as we know, is the decomposition or the breakdown of a compound using electricity. Okay. So basically, since this is electrolysis, then we have some stuff formed at the cathode and some other stuff formed at the anode. So basically, at the cathode, here the aluminium ion receives electrons to become atoms again. So aluminium ion with receiving electrons becoming an atom again. And at the anode, the oxide ions lose electrons to become oxygen molecules. The oxide ions loses electrons to become oxygen molecules. And here we have another question. It's a fact with a question. A fact that anode is replaced periodically. But why is anode replaced periodically? Because carbon reacts with oxygen at high temperatures, and so it forms carbon monoxide and carbon dioxide. That's why anode is replaced periodically. I'm not sure why it's this, but okay. Send me cards. So we did a very quick recap. We also explained how metals are extracted. We're done with extraction of aluminium. We now have the uses of aluminium. The uses of aluminium are like aluminium is used in aircrafts as it has low density and strength. Because it has low density and strength, it makes it ideal for construction of aircraft and lightweight vehicles and ladders. So basically, it's because it's low density and strength, it's used in aircraft, lightweight vehicles and ladders. And also for food containers, because it's corrosion resistance and has low density. Because it's corrosion resistance and it's not poisonous, it's used in food containers. Also, it's used in greenhouses and window frames because it's corrosion resistance and has low density. It's used in cookers and cookware and boilers because it's a good conductor of heat. It's a good conductor of electricity. That's why it's used in overhead power cables, which is like electric power lines. And here in this point, low density gives it an advantage over copper. Basically, also we have drinking cans because they're corrosion resistant and they're easy shaping. Also, it improves properties because it's an alloy. There is an alloy of aluminium called duralumin, is often used instead of pure aluminium to improve properties. And this is we're gonna talk about it later in alloys, just after the extraction of iron. So basically, these are the uses of aluminium. I wrote them down over here. So now let's start in extraction of iron. Let me write it with you guys because why not? I don't know how to really use this kind of font, so anyways, extraction of iron. Okay. Extraction of iron will be completely different because we extracted aluminium by electrolysis. However, extraction of iron will be with copper, in reacting it with copper, I think, in the blast furnace. I'm not sure if I used the word reacting or the word reactant is the best word or not. However, it is with carbon in the blast furnace. Okay. Bye-bye. Okay, so basically this looks a little bit like filling in the blanks. However, we're gonna explain this way this time. The ore is called hematite, and it consists of 60% of iron in form of iron oxide. However, it's mixed with other impurities such as silicon dioxide, and the process takes place in what we call by blast furnace. So as we can see over here, we have 5 raw materials used, and they're very, 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 very important. We have first the ore, which is the hematite, and we have coke carbon, which is fossil. We also have limestone, which is calcium carbonate. We have warm air as a source of oxygen. We also have water as a coolant. These are very, very, very important. Also, the temperature used is from 1700 Celsius to 2000 Celsius. We use coke carbon, which is fossil, because to increase the temperature inside the furnace to 2700 Celsius, and also to react with oxygen to produce carbon dioxide, which reduces the ore. Carbon dioxide plus nitrogen are waste gases. Generally, carbon dioxide produced and nitrogen are waste gases. So now let's study the equations for extraction of iron. They are very, very important too. So basically, first here we have the carbon. Here's carbon, and it reacts with oxygen from warm air, producing carbon dioxide with heat, and this is an exothermic reaction. Now carbon dioxide, which is the product, is now the reactant. Okay, it reacts with carbon again, forming carbon monoxide. Now the iron 2O3 oxide, which is from the ore, reacts with carbon monoxide, forming iron only and carbon dioxide. So basically this is a redox reaction. As you can see here, it some loss, some gains, and then now the last step, the fourth step, which is calcium carbonate, which is limestone here, thermal decomposition happens to it, so it's divided into calcium oxide with carbon dioxide. Now calcium oxide here, it's the product, now it's the reactant. Gets mixed with the silicon oxide, which is already in the ore, and here it's an impurity, okay, to form calcium silicon dioxide. Anyway, this is a slag. Okay, this is a slag, and it forms above molten iron. This reaction is called neutralization, and it's in the acid-base chapter. This is called thermal decomposition. Here, redox reaction. Here, we said that it's a reducing agent over here, and over here, this is the exothermic reaction. We're now let's go to our checklist here. We're done with extraction of iron as well. We now have alloys, mainly. Okay, so we're just having alloys right now, and the purification of copper. Okay, so now let's talk about the alloys. So basically, you need to describe an alloy as a mixture of metal with other elements. It's mostly, or maybe you can say that it's a mixture of 2 or more metals, or metal with a non-metal, such as, for example, carbon. So basically, for example, brass, you need to also describe brass as a mixture of copper and zinc, and stainless steel as a mixture of iron and other elements such as chromium, nickel, and carbon. So basically, an alloy is a mixture of metal that changes their properties or increase them. Turning a metal into an alloy increases its number of uses. Alloy is formed by mixing molten or metals together, then cooled. So we use an alloy to increase strength and some to resist corrosion. And we have examples. Also, they're mentioned in the syllabus. They're very important to know. Number 1 is brass, as we said. It's copper and zinc. Number 2, is stainless steel. It's chromium, I think. Let me just write it. It's chromium, nickel, and carbon. So alloys can be harder and stronger than the pure metals, and they are more useful. That's why we make these mixes. Okay, so when we have a soft or a when we have a soft metal, for example iron, is too soft and stretches easily and it rusts. So when you mix it with a non-metal, for example like carbon, mild steel is formed, and this is very hard and strong. It's hard actually and strong. So for example, another example is when nickel and chromium are mixed with iron, the result is stainless steel, and this is hard and rust proof. So also a point in the syllabus is that to describe the uses of alloys in terms of their physical properties, including stainless steel in cutlery. So stainless steel is used in cutlery because they are hard and resistance to rusting. And these properties were formed because they are alloys. They are a mix. You get a very good thing in something, and a very other good thing in something, and a very other good thing in something. You mix them together, forming an alloy, which is a very, very good element or a mixture that is mainly used in a lot of stuff because it has better physical properties. So now we have 2 points that mainly talks about the diagram of the structure of the alloys. So before we draw the diagram, you need to know that alloys can be harder and stronger than the pure metal because the different sized atoms in alloys means that the layers can no longer slide over each other. So they are very hard and stronger. And we have also the diagram to draw. So let's draw them together. These are big, for example, and then you have smaller ones. You have a red one in between. Then imagine this color is the same as this. Anyways, then you have smaller ones. Then you have a red one again. Then you have blue again. Then you have maybe big ones, smaller ones, then big one, then smaller ones, then medium ones, medium, then red one, then yet smaller ones. So these are the alloys. They are very different in their in the size of their atoms. That's why they're stronger and harder. Their layers cannot slide over each other. They are different in their sizes. So basically, why alloys are less malleable? It's the same question in different form right now. However, it can come in this way. Why alloys are less malleable? Let me just mention that these are exam questions. Because due to their difference in particle sizes of atoms, the atom radius, and so layers can't slide over each other, so they gives strength. Also, another exam question or another point that you need to know is that carbon is the only non-metal in alloys. It gives strength, but when carbon increases, it makes the alloy brittle. So we have other alloys to know. We have brass, that it's made up of copper and zinc. It's harder than copper, and gold colored. Musical instruments, ornaments, electrical connections are their uses. We have also bronze. It's from copper and tin. It's harder than copper, and it's used in bells and machine parts. We have mild steel, which is made up of iron and carbon. It's strong and harder than pure iron, and it's used in car bodies. Stainless steel is made up of iron, chromium, and nickel. It's harder than pure iron, does not rust. They are used in cutlery, surgical instruments, reaction vessels in the chemical industries. Also, we have solder. Solder is made up of tin and lead, 50%, 50%. Lower melting point than either tin or lead, and they're used in making electrical connections. So basically, brass is copper and zinc, 70%, 30%. Bronze is copper and tin, 90%, 10%. Mild steel is iron and carbon, 99.7%, 0.3%. Stainless steel for iron is 74%. Chromium is 18%. Nickel is 8%. Solder is 10, and lead 10 is 50%. Lead is 50%. So as we can see over here, steel hardness depends on the carbon percentage. As we said, the carbon gives strength, but when the carbon increases, it makes the alloy brittle. The only non-metal element in the alloys is carbon. Now we're done. We're done with alloys. Here, we're done with alloys. The only thing left is the purification of copper. Let's go. Hello friends, we're now having only purification of copper. Basically, it's the electrolysis of copper to sulfate solution. Anyways, we call it also purification of copper. So basically, here in this thing, you can say that it's electrolysis, right? So we have the anode, we have anode, and we have the cathode. And at the anode, we have impure copper. So the copper is made, the anode is made of impure copper, zinc, and silver combined, so it's impure. And the cathode is made of pure copper. So while electrolysis, here we have, for example, these are random numbers. We have, for example, 10% zinc. We have 70% copper, and we have the 20% silver. So we basically, when electrolysis goes, this copper goes to solution to go to the cathode, so that the anode size was like this. It starts decreasing, and the cathode size starts increasing because more copper goes to the cathode. So because cathode is made of pure copper, anode's mass gets smaller and cathode's mass gets bigger as copper ions in the anode leaves. Because oxidation occurs, it's at the anode, right? So OAA, so oxidation occurs for the copper ions, so it goes to the cathode by going through the solution here, and basically now at the cathode is now pure copper metal, not ions. Okay. We have also ions from copper to sulfate, which are copper 2 and sulfate. And we have ions of water, which are H positive and hydroxide negative. So at the anode, the hydroxide ions and the sulfate ions are attracted to the anode. The hydroxide ions give up electrons more readily than sulfate ions. Consequently, the hydroxide ions are preferentially discharged to give oxygen gas. Okay, we said this in the first chapter, that we have the first part, that we have molten, we have solution, and this is solution, and so oxygen is what is discharged. Like, oxygen is the gas given. here is the equation for OH hydroxide, giving us water, oxygen, and the 4E minus. And so the SO4, the sulfate, remains in solution. That's of course at the anode. I just want to check that I said we have molten and we have aqueous, and then aqueous we have dilated and we have diluted and we have concentrated. So basically this what were the ions at the anode. We have here ions at cathode as well. The hydrogen positive ions and the copper positive ions are attracted to the cathode. So copper, as you know, is lower in the reactivity series than hydrogen. So as we said before, the least reactive is the one that is the one that we write for the equation at the very end in the cathode side. So basically here, since copper is less reactive in the reactivity series, copper 2 ions accept electrons more readily than hydrogen ions as a result. So copper 2 ions are preferentially discharged as copper metal atoms. So this is the equation, the Cu positive plus 2E minus, giving us copper. And the hydrogen ions remain in solution. Hydrogen ions remain in solution. So we have over here that has impure, and anode is impure copper that has zinc and has silver and has copper, and cathode is pure copper. And so when the copper goes to the cathode, it goes as metal atoms, not as ions. So basically a cathode gets bigger and anode gets smaller. So basically, as we said, sulfate remains in solution, and so the impurities, for example like zinc, also remains in solution. The zinc impurity in the impure anode drops down into the solution and mixes and dissolves. So when you have zinc, so zinc is the impure thing, okay? And we had already copper sulfate, right? So because zinc is higher in their activity than copper, it displaces the copper and makes it zinc sulfate with copper. Copper is now an atom, impure one, and now it's zinc sulfate in the solution. So because so now the product part is zinc ions and sulfate ions. And for the sulfur impurity in the impure anode drops down without dissolving and creates the silver sludge you see at the bottom, as there is no reaction between silver and sulfate, because as well as you know, silver is already lower than copper, and so it's lower than zinc. So also the silver impurity drops down, however it does not dissolve, and it creates only the sludge you see at the bottom, as there's no reaction between the silver and the sulfate. So as a quick very summary, when aqueous copper 2 sulfate is electrolyzed using the platinum electrodes, copper metal is deposited at the cathode and oxygen gas is given off at the anode. And here is our overall reaction. We have the copper sulfate we're electrolyzing and with water. So at the very end we have copper, pure copper, with oxygen, with sulfuric acid, I guess. And this is all. Also you need to know that at the anode we have impure copper, at the cathode we have pure copper. And that's it. Bye bye.